Hello again, everyone. Thank you for being here. This talk is a bit of a story about how I built a serverless video transcoder using Lambda, step functions, S3, EFS, and DynamoDB. But first, let me reintroduce myself. My name is Sbarski, and I'm one of the co-organizers of this event. My day job is VP of Education and Research at A Cloud Guru, and I also happen to be an AWS Serverless hero. A few years ago, I wrote a book called Serverless Architectures on AWS, and that has been my one claim to fame ever since. Last year, Nikki Stone and I were planning a talk for ServerlessConf, which is a big, dedicated serverless conference. And we were trying to figure out a good topic. One idea that came to mind was around solving genuinely big problems with a pure serverless approach. If you have a task that takes more than 15 minutes to process, what can you do? And so from that discussion came an idea to build a serverless video transcoder to transcode large video files. Our proof of concept would take a video file and then transcode it to another format or another bitrate or resolution. And the thing is, we would only use Lambda as our compute option. No containers, no EC2s. So how would this serverless transcoder even work? We knew that the only true way to process large tasks of this nature would be to break them up into smaller tasks, process these smaller tasks independently, which could be done with Lambda, and then combine them together to get a result. As you have already guessed, we took our inspiration from MapReduce. So here are the general steps you would need to go through if you wanted to transcode a video. So first you have your original file. Then you split it up using Lambda. Then you transcode each smaller portion in Lambda. Hopefully you can do this in parallel. Then you begin to merge transcoded segments together. And at the end, you have your final video merged, combined together that has that different bitrate or different encoding. So we actually implemented this and it worked. And I'm about to present you our architecture. I have to warn you that it is simplified because I wanted to illustrate just the main steps. So for instance, I'm not really showing DynamoDB, which is used to maintain state. Also, I should mention that we used FFmpeg to actually do the splitting, transcoding, and merging of files. We ran FFmpeg as a Lambda layer, which worked very well. So here are the main steps. First, you upload video file to S3. Easy enough. That kicks off a Lambda function that analyzes the file and figures out how to split it up based on keyframes. The analyze video function sends an event to an SNS topic that invokes an extract audio function that, as you have already guessed, extracts and saves the audio file to an S3 bucket. The analyze video function also sends a whole bunch of messages to another SNS topic. SNS fans out and invokes a large number of lambdas that begin splitting up the video and saving those tiny little segments to another S3 bucket. We actually combine the splitting operation together with the transcode operation. Both of these things happen within the same execution context. And it really made things easier for us to manage and maintain. Once new segments are created and transcoded, the merge operation begins. Neighboring segments are merged together until everything has been merged into one and that new video file has been produced. A nice property of our system is that pairs of segments can begin that merging process as soon as they are ready. We don't actually need for the entire split operation to finish before certain segments can start merging. So that's kind of nice. Finally, the new video is merged, like I said, and it's combined together with the sound file that we had saved earlier. The final file, which consists of video and audio, is uploaded to an S3 bucket. The cool thing about this solution is that it is entirely event-driven, it's entirely push-based. You just upload the file, and then you get another file in another S3 bucket at the end. We ran a whole bunch of tests and got pretty good results. We compared a number of files to a large T2 instance and to my own MacBook Pro, which is actually the computer I'm using right now. So let me show you the results. And here we are converting different files to 720p. So here are the results for the MacBook Pro, which is a pretty reasonable machine with 16 gigs of RAM. Here are the results for the EC2 instance. So we used T2. We probably should have used a C4 instance. And so I think I may actually rerun these tests again with C4. But here are the results for our serverless Lambda. And you can see that in all cases but one, our serverless Lambda implementation actually beats EC2s and the MacBook Pro. I have to note that our proof of concept isn't especially optimized, and I'm sure more can be done to improve it. And I want to do a call out. If you are an FFmpeg expert, please reach out to me. I'd love to talk to you. I am sure that I'm not using FFmpeg to the best of its capability. There are a few interesting challenges and improvements that I have made since then. These relate to maintaining state, managing the workflow, and storing temporary files, or segments as I call them. So let's briefly talk about them now. As I mentioned previously, we use DynamoDB to maintain state. It helps us know which segments have been created and which have been merged. It helps us kick off a merge operation once we know that the two neighboring segments are ready. DynamoDB has actually been excellent for this. It's fast, it is easy to use. We also set a TTL on all records so that they are automatically deleted after a few hours. It helps to keep our database nice and clean, which is excellent. When we did our presentation at ServerlessConf, I remember somebody in the audience asking, why are you manually doing parallel fan-out with SNS when you could be using step functions and dynamic parallelism? So dynamic parallelism was a newish feature that had been announced about a month before the conference. And honestly, I didn't get a chance to explore it in any kind of depth. However, since then, I have re-implemented our serverless transcoder to use step functions, and it works a treat. I got rid of SNS completely, and now I dispatch a list of tasks that are processed by Lambda in parallel, and all of it is managed by step functions. And the nice thing is that you have visibility into what's happening. You can trust each task, you can look at all inputs and outputs and see whether anything has failed. Step functions has its quirks. It's pricey and it can be tricky to restart a particular task from the point where it failed. But I am very happy overall. I feel like I have a more robust system that also gives me more visibility. So the lesson is, if you are building a MapReduce system yourself, or if you're doing complex fan-out operations, consider using step functions. For your particular use case, it could be, a more robust solution as well. The original implementation that I created stored all files, including all temporary segments, in S3. So whenever a segment was created, a function would upload it to an S3 bucket. Luckily, we can use S3 streaming, so you don't need to write a file to local disk in Lambda and then upload it to S3 as two separate steps. You can actually create a file and stream it to S3 as kind of a single step, which is nice. But still, it's, a little finicky. AWS told me that EFS support for Lambda was coming, and I got excited about that. And luckily, AWS allowed me to participate in the beta. And so I re-implemented the serverless transcoder with EFS instead of S3 and learned a few things. So first of all, I think EFS made my implementation a little bit simpler, a little easier. Instead of reading and writing to S3, EFS presents itself as a local file system that you can write and read. It's effortless once it's configured, and it is basically endless disk space. It's amazing. I need to do more tests, but EFS unfortunately is likely going to be much more expensive than S3 for my use case. I also need to compare performance of EFS to S3, and once I have my benchmarks, I will publish them online. But apart from the cost and performance, which again I need to measure, I think that EFS for Lambda opens up a whole new world of possibilities. You can now run applications and tasks in Lambda that you couldn't have before. Having said that, EFS will cause issues because people will use it to maintain state and build crazy things like databases on Lambda. In my case, moving to EFS from S3, I don't know, you kind of lose the notifications feature of S3, you lose access logs. So whether there's a big benefit, it's still an open question for me. I suspect that it is better to stick with S3, but I'll know for sure once I have done more analysis. So my lesson here is just be thoughtful about it and try to choose the right tool for the right job. I've written more of my thoughts, which you can read on this blog at A Cloud Guru. I will be releasing all my source code on GitHub and an in-depth chapter about this in the second edition of my book. If you have any questions, please feel free to DM me on Twitter and I'd be happy to chat to you. Thank you for listening. Thank you for attending our serverless community day. Thank you.